All right, well, let's get started today. First, I want to thank everyone for joining me for our webinar today on condition monitoring. Don't have stored fuel without it. I am Eric Bjornstad, Technical Information Director here at Bell Performance. And, 2018 has been a pretty big year for us. It's been a big year for everybody across the country that has stored fuel. And when I say big year, I mean a significant year, because the changes in the industry that have been kind of developing and fomenting over the last 3 or 4 or 5 years, those changes are now coming to roost. And people are finding that they need to change their approach when it comes to managing their stored fuel, especially if they have mission-critical stored fuel. So in our time together today, we are going to talk about the vitally important issue of condition monitoring for stored fuels. So in our time together, our overall goal in that time is going to be to give you a better understanding of what condition monitoring is all about. So that means the whats and the whys and the hows of the subject. So we will start with some context on the basics of fuel microbiology. Okay? Then we'll jump into the issue of what condition monitoring actually is, why it's important, what considerations need to be included in our planning on the subject. And that means we will need to talk about fuel sampling, how you should be sampling your fuel, why it's important to do that, because those are all important factors to get us to our end goal if we're doing mission-critical fuel management. And that end goal is making sure that we know the true condition of our stored fuel so that we can know if action needs to be taken. And as we look closer at this kind of subject, one thing we should come to realize is that when it comes to microbes and the world around us, things are rarely as simple as they might first seem, and they also aren't as simple as we might want them to be. So let's dive in by taking a brief overview of fuel microbiology so that we can set the stage for the whys of condition monitoring. Now, when discussing this type of subject, we usually start out by laying out the justification for why we need to be talking about it. That means we need to be talking about what this problem costs businesses and fuel users across the country. Now, the costs for microbe-related corrosion are pretty substantial, and that's both on a national level, where countrywide costs for corrosion can come to $270 billion or more, and also the ground level or the field level, where if you are a C-store at a gas station, you can lose between 5 and 20% of your fueling revenue because of slow flow rates that are linked to fuel-related microbes. And then there's catastrophic costs like site remediation expenses if you have a leaking storage tank, which can happen if you have severe corrosion. If that happens, you're looking at baseline between $200,000 and $500,000 per site, and then, of course, depending on the details, it can go up from there. And that appears to be what has happened with these people in that picture that had they are residential, but still they had a fuel oil storage tank that leaked because of severe corrosion, and now they're having to do what you're seeing in that picture. So it's clear that if left uncontrolled, microbial contamination in fuel systems is linked to a number of expensive problems. So let's look now at the microbes themselves and what those microbes do in fuel systems and storage tanks. Now, as we all remember from science class, microbes are single-celled organisms. They're too small to be seen with the naked eye, and they include classes, bacteria, fungi, which are the ones that get invited to all the best parties, viruses, archaea, algae, and protozoa. Now, you will not find all of these types in every single place. When you're looking at fuel or fuel system samples, it's rare to find, let's say, protozoa or algae. So we are trying to frame this in the context of fuel microbiology, the microbes we concentrated on are the bacteria and the fungi. Now, even among these basic categories, there are subcategories that reflect what these microbes need to grow and what they do to the environment around them. You have aerobic versus anaerobic microbes. Aerobics require an oxygen-rich environment to live, while anaerobics requires an oxygen-free environment. You've got microaerophiles, which are microbes that only need some oxygen, but they can't tolerate too much. There's what they call facultative anaerobes that kind of start out living and multiplying in an oxygen-rich environment, and then they use up the oxygen and help create more of an oxygen-poor environment that other kinds of microbes use to grow. And there's also a major class of bacteria called sulfate reducers. Sometimes they're abbreviated as SRBs, sulfate-reducing bacteria. These consume SO4 molecules, and they contribute to microbial-induced corrosion in a pretty substantial way. Now, in a given fuel tank, you have thousands of different kinds of microbes, and they all really require the presence of each other in order to grow and thrive. That is why microbiologists talk about microbial colonies being really more like an ecosystem or a biosphere in their own right. Now, there are so many microbes on us and around us, it is virtually impossible to be microbe-free anywhere. Hence, that's never really the practical goal in anything. The goal is always to have a manageable level of microbial presence. That, of course, begs the question: how is a manageable level defined, right? Think about things like this. Even in drinking water, like treated water that's safe to drink, in every single drop of that, it's not uncommon for there to be between 10,000 and 1 million microbes in a single milliliter, in every single drop of that. Now, zoom in a little bit more specifically to what we're concentrating on. Look at the water bottom samples in storage tanks. How many microbes are in that? Well, again, for every milliliter, you can actually increase the previous number by 1,000-fold. There can be up to 1 billion microbes per milliliter in storage tank water. So there are so many microbes surrounding us everywhere we go, every second of every day. Nobody should ever be surprised when they find microbial presence pretty much everywhere or anywhere, and that includes in fuel systems and storage tanks. Now, since we find microbes in fuel systems and storage tanks all the time, it is fair to ask the question of how they got in there. And when you're asking that, you're really, in order to get the best answer, you really need to look at it in two ways. You need to look at how microbes get into storage tanks and how they get into the fuel distribution system that precedes the storage tanks. Now, for storage tanks, there's lots of ways for microbes to get in there. Anything that enters that storage tank likely will have some level of microbial growth in it or on it. So whether you're talking about water ingress from either a leak or a spill bucket or even from a fuel dump, or even just something as simple as water vapor and dust that's in the air that you can't even see, that has significant microbial presence on it. And if you look at larger storage tanks at fuel terminals, the kinds that have those floating roofs that go up and down depending on the level of product in it, as fuel is drawn down, you create a vacuum that pulls these materials into the vented tanks, plus that can actually scrape outside microbial presence from the natural world down into the product. So, there's bottom line. There's lots of ways for microbes to get into storage tanks. Now, the distribution system, the fuel distribution system, we typically start at the refinery because that's the starting point for all this. And at the refinery, the fuel is actually sterile when it's first put together, right? Because of the high temperatures that are involved in that. But it is only sterile for a short period of time because it's going to go into a refinery bulk tank, which is not sterile. Then it's going to go into ships, which are definitely not sterile. And consider the fact that ships often use water for ballast. Well, there's lots of microbes associated with that, right? You have pipelines and rail cars, and so this fuel then goes out to fuel depots where their tanks are not sterile, and then it's sent out for local and regional distribution. Now, consider also that these fuel depots, they get and they aggregate fuel from lots of refineries, like 100 different refineries. And that means that if you have fuel coming from just one of those, and there's microbial growth or biomass or presence anywhere at that site, some of those microbes are going to be carried into the fuel from all of those other places. So it should be pretty easy to see that it's really easy to have microbial growth develop at lots of different points along the way. Now, ultimately, we are most concerned with end-user fuel storage tanks and what microbes do there. So, for those places, where do microbes live in those kind of fuel systems and storage tanks? Now, when we're talking about microbes, we are accustomed to describing how microbes like to grow and reproduce at the interface between the fuel and the water. But most commonly, their preferred place is growing within biofilms that are located on solid surfaces. Now, these biofilms are not evenly distributed within any given storage tank. In any storage tank you look in, there's always going to be areas of high concentration of this kind of microbial biofilm because of what the microbes prefer to use inside of the tank for growth and reproduction, reconciling that with what's available for them to use within that given tank. So bottom line there is that virtually all storage tanks have some kind of microbial growth and biofilm in them, but it's typically unevenly distributed. I guess if you wanted to pick a place that has the highest concentration, it's going to be bottom dead center, about 15 degrees plus or minus. Now, contrary to our perception, these biofilms that we were just talking about, they are not uniform. They're actually a lot more complex than we give them credit for, and that's both in internal composition and also in their distribution within a storage tank. So, as I was just alluding to, it is not uncommon to look inside a storage tank like a UST and have kind of like zones of heavy biofilm coverage that are next to zones that may appear to be pretty clean. Now, these biofilms can have significant variance in their thickness. And so what that means, the reason why we're bringing this up, is it means that samples that are taken from different parts of the same biomass formation, those can actually give you vastly different pictures of the microbial presence in the tank. So, and that means that where and how you sample here controls what you detect. We're going to touch on that in more detail later, but that's an important point to keep in mind. Now, within any given biofilm, right, there can be a pretty diverse assortment of microbes. It's what they would call a heterogeneous situation. And these microbes exist in symbiotic relationship with each other. Different kinds of microbes in different locations of the biofilm. Now, what are the implications here for sampling? Well, we said earlier that microbes like to grow best in biofilms on solid surfaces. Now, the implications for sampling is that if you take a sample of a biofilm from a solid surface, right, and you're going to record a number of microbes from that sample, you're trying to figure out the question how representative is this sample of the overall picture within the tank? Well, the short answer to that is that there can be significant variance depending on where you sample. what we've been kind of alluding to is the fact that because microbes like to grow inside these biofilms, because different kinds of microbes like to have different kinds of things around them in order to grow best. A biofilm can have completely different environment within it than outside. And it can also have a different environment in different parts of the same formation. Now, when we're talking about environments, we're talking about things like it can be more acidic. It can have different oxygen contents. It can have different sulfur contents, not just different to what's in the outside environment of the tank itself, but also different within different parts of the biofilm. This is the kind of thing that we've been alluding to when we said things are more complex than they might appear, right? So a biofilm formation within a storage tank is a perfect scenario for when you need to have 1,000 different species of organisms, all requiring differing levels of different things to grow, all depending on each other in order to live life to the fullest, so to speak. Now, up to this point, we haven't really touched on in any detail on what happens as these microbes are growing and reproducing. Namely, how are they affecting and interacting with the environment around them? For one thing, microbes produce different types of metabolites, different substances from their metabolism, from their metabolic processes. And a number of these metabolites can have deleterious effects, negative effects, on fuel and storage tanks. They produce things like short-chain carboxylic acids and acidic alcohols and different kinds of sulfates and salts. They can form these weak organic acids, which are bad because those acids, once they're formed, they then will react with things like aggressive chlorine ions or other kinds of aggressive ions, and they'll go from weak acids to strong acids like sulfuric and hydrochloric. Then there's these things called biosurfactants. If you ever need a cool word to use in Scrabble, you can bust out the word zwitterion. That will get you a lot of points. Biosurfactants are important for microbes. Biosurfactants are organic molecules, and they have an electric charge on one end, which makes that end attracted to things like water. And then on the other end, they don't have an electric charge, which makes them attracted to things like fuel. So one end is polar, the other end is non-polar. Have you ever heard the joke about why are white bears attracted to each other? Well, it's because they're polar, right? Yeah, so that's today's the bad joke for today. So microbes produce these biosurfactants, and they use them to help disperse water into the fuel, or rather the other way around. They use them to help get into the fuel so that they can get at the food molecules in the fuel more easily. And so when this happens, there's emulsions or inverse emulsions that are formed, and that's one of the things that makes fuel hazy. Now, speaking of emulsifying water, making fuel hazy, we've touched on an important thing. What effect do microbes have on the fuel and on the environment around them? Well, generally speaking, the effect that microbes have on different kinds of fuel depends on the fuel itself. Now, let's say gasoline, for example. For years, it was thought that microbes didn't like to grow in gasoline. The reasoning for this was scientists thought that the low-end hydrocarbons, the lighter hydrocarbons like the C4s through the C7s, those are constituents in gasoline. They actually thought that these hydrocarbons were toxic to microbes, but they know now that this isn't the case at all. There are plenty of kinds of microbes that like to consume these low-end molecules. They use them for fuel. Not only do they do that, but they also consume the oxygenate, and we all know that gasoline today contains oxygenate. Now, when they consume these low molecular weight molecules, these low-end hydrocarbons, it changes the molecular distribution or composition of the fuel, right? They're consuming more of the low end, which means the distribution is now made up of more heavier molecules. And that also changes the proportional percentage of aromatics, because microbes, they don't like to consume aromatics, they like to consume the straight chains, the aliphatics. And so when they consume and destroy the aliphatics, the aromatics that are left are now, of course, a higher percentage of the fuel blend. So the effects on the fuel itself, you've got things like a change in vapor pressure and a change in viscosity of the gasoline over time. Now, what about diesel fuel? It's a lot more common to find microbes and their associated water phases in diesel fuel storage tanks. So what's happening when we find them there? Well, while microbes can live freely in fuel, in liquid fuel, or what they might call, they can live planktonically in there, they typically need some kind of free water available if they want to grow and multiply. And it does not take much water at all for microbes to do this. Now, when we were talking about biofilms earlier, one of the things that we should have mentioned is that biofilm, and we're talking about this in the context of how easy it is for microbial communities to live in biofilms. Basically, no matter how small you think a biofilm is, it's plenty big enough for lots of microbes to live in there. Now, consider water phases. If you have a 1/8 of an inch water phase height, and you have a microbe that's living in that water phase, that 1/8 inch water phase is the size equivalent of a mountain like Mount Kilimanjaro, relative to a human being looking at it. So a single microbe in 1/8 of an inch of water it's basically like a mountain in terms of the height. So when we talk about that, and we also bring up the fact that we mentioned earlier, that 1 milliliter of water is enough to support between 1 million and 1 billion microbes, that makes it obvious to us that it does not take much free water at all to support plenty of microbial growth. So when you get a free water phase that builds up under the fuel, the microbes are going to do certain things in order to use that water for their benefit. First thing that happens is that there are going to be polar molecules that will start to move from the fuel into the water. And when that happens, the microbes will be there to use them in part for fuel. Then, of course, the microbes do what we just mentioned. They produce those biosurfactants. And the biosurfactants then enable water to emulsify and go up into the fuel, so you now have the creation of an invert emulsion. So then the microbes like invert emulsions, because microbes will then transition up into that invert emulsion, where they have better access to the surrounding fuel molecules for use as fuel, right? And no talk about microbes would be complete without examining the effects that they have on the tanks and the storage environment that they're in. And when we start talking about this, we typically bring up terms like fouling and corrosion, right? Now, we are used to thinking about corrosion as the thing that it's the thing that happens with microbes in storage tanks. But it's not quite as simple as that, because in order for corrosion to happen, you have to have metal. Well, what about the non-metallic parts of the tank, of which there are plenty? Well, let's talk a little bit about non-corrosive effects. Non-corrosive effects are things like fouling, when you have slime or biofilm that's free-floating, and it starts to accumulate non-uniformly on certain kinds of fuel system surfaces, including fuel filters and also on the tank float itself. If it gets on or in the tank float, it will actually change the float's specific gravity, which actually causes that to give an inaccurate volume reading. Talk about non-corrosive damage tank linings. Microbes can definitely damage tank linings. Let's say you have a scenario where you get a pinhole leak, a pinhole compromise of the surface. Well, a pinhole is plenty big enough for lots of things to happen. What happens is that fungus actually gets into that pinhole and then goes up underneath the lining. And at the same time, you also have moisture that will go into the pinhole and then up underneath the lining. Now, as temperatures change, the moisture will expand and contract, and that will start to compromise or delaminate the lining from the tank shell. And eventually you have this blistering, you can have this peeling, and so that's non-corrosive damage. And microbes like fungi can also compromise fiberglass tank surfaces simply by establishing themselves on the surface, then penetrating the resin, and then consuming the resin, which deplasticizes that fiberglass, creates more gaps for additional microbes and for additional moisture to get in there, and now you have a huge problem. So those are the kinds of non-corrosive damage issues that can happen in storage tanks with microbes. Now, anytime you have metal surfaces and metallic components in storage tanks, you're going to have corrosion mechanisms at play, damaging the tank. Well, what are these corrosion mechanisms? Well, with corrosion, the most prevalent mechanism for observed tank corrosion in the wetted area, we're talking about corrosion under the fuel, the fuel line, as opposed to vapor space corrosion. So we're talking about wetted corrosion. The most prevalent mechanism for this is when you have the formation of a galvanic couple that happens between the steel or the metal in the tank, and then something like if you have iron sulfide ions that have been produced by microbes. So you have a galvanic couple, which this kind of thing can happen. Remember, way back when we mentioned sulfate-reducing microbes, sulfate-reducing bacteria, and we said they play a significant role in tank corrosion. Well, this is one of the ways that they do that. They help the formation of galvanic couples, which causes accelerated corrosion reactions to happen. Now, the presence of biofilm on metallic surfaces also plays a key role in promoting corrosive damage. That is why it is so important to address and get rid of biofilm. A lot of people think, biofilm doesn't matter as long as it's not plugging my filters, it's okay. Well, it's not okay because biofilm plays a key role in tank corrosion damage. What can happen is if you have layers or patches of biofilm that are on the tank surface, you get the creation of electropotential gradients between the covered parts and the uncovered parts. So you get a difference in the electrical potential between those two areas. That leads to galvanic corrosion and the creation of pinhole leaks like what you see in that electromicrograph picture there. Oxygen. Presence of oxygen also plays a key role in the development of corrosion damage. Many people don't realize that when you're comparing hydrocarbons, like diesel fuel, for example, and you're comparing that to water, oxygen's actually a lot more soluble in fuel than it is in water. Fuel can typically dissolve upwards of about, let's say, 60 parts per million of oxygen, whereas water can dissolve about 8 parts per million. So what happens here is that oxygen will actually, through the principle of osmosis, things like to move, provided there is a way for them to actually move, things will move from areas of high concentration to areas of low concentration. And so what happens is when you get water and fuel, oxygen will want to diffuse or move from the fuel, where it's high concentration, into the water phase to try and even things out. Now, that in and of itself, not a big deal. But when you have biofilm that's nearby, what will happen then is that oxygen will actually get trapped by the biofilm, and you will get the creation of an area, a kind of a localized area where the oxygen concentration is pretty high. That produces localized corrosion and metal loss. Same thing can also happen if you have, with carbon dioxide too. Gets trapped, you get pockets of carbon dioxide which form carbonic acid, which is extremely corrosive. Another thing, if you have in the tank water bottoms, if you have high sodium levels, and this is interesting, if the sodium levels in the tank bottom exceed, let's say, 0.1%, which is about 1,000 parts per million, if you get a high sodium level, this is linked to corrosion and to what they call soap formation. The acidic components, which are produced by the microbes, remember, those will combine with the sodium and they will form these chemical soaps. Now, what these soaps do is they actually attack the corrosion inhibitors that have been added to the fuel, and they inactivate them, they break them down, which then makes it easier for corrosion to happen. So those are some of the corrosion mechanisms. Again, remember when we said things are more complicated than they appear? Well, once you start considering things like that, you realize that these mechanisms can be pretty complex. And of course, no discussion of corrosion and microbes would be complete without talking about the acid-producing bacteria themselves. Now, acid-producing bacteria, what they typically do is they produce short-chain fatty acids and low molecular weight acids, things like acetic acid and formic acid and lactic acid. Now, what these bacteria will do, and this is where we start talking about vapor space corrosion. What they'll do is they will actually use vapors, the hydrocarbon vapors. They will actually use them as fuel, and they will actually then create colonies in the tank overheads, where you also not only do you have these fuel vapors, you also have water condensation. And so what you can have happen is you can actually have the formation of biomass formations that are almost hang down like stalactites. The ASTM D6469, which is the standard guide for microbial contamination in fuels, actually references that phenomenon. So you have things like that can happen. There are other bacterial species which produce aggressive inorganic acids like sulfuric acid. And, like we said earlier, they contribute to localized high concentrations of carbon dioxide, which dissolves in water and produces corrosive carbonic acid. Now, having mentioned all of this, one other thing to keep in mind, it is not uncommon to have actual microbial activity in your tank, and yet at the same time, your fuel passes the NACE standard. So that's just one thing to keep in mind, because some people will say, well, my fuel passes the NACE standard, therefore I don't have a microbial problem or don't have microbial presence. And one definitely does not follow from the other. So how quickly does corrosion happen in a typical tank? Well, if you're looking at like the average literature value for corrosion rates, you're talking about 0.3 to 0.5 millimeters per year. And this is for diesel tanks. Gasoline tanks actually have lower corrosion rates, only around the 10th of a millimeter per year. Now, part of the nature of the kind of tank corrosion damage and fouling and microbial-induced corrosion, or MIC, that we've been talking about or looking at here, part of the nature of this is you rarely will find it unless you are actually looking for it. That means you rarely find corrosion damage before it's developed to the point where the problems are obvious. That fact gives us an excellent reason to look closer at the essential practice of condition monitoring in our fuel storage systems. So that is what we are going to transition to next. At its heart, when we refer to condition monitoring, we're talking about methods that we can use to detect any changes in the condition of our stored fuel and our storage tanks that might hint that there's something wrong. And we tend to find that at the heart of most changes in stored fuel condition are fuel microbes. These problem-causing microbes are often undetected because of either incorrect sampling or incorrect testing, or some combination of the two. Now, if you were trying to pick which one was the bigger problem, uh, sampling would be the greater issue of the two. Okay, so how do we not fall into this trap of not noticing anything until the problem's actually too big? Well, detecting microbial contamination in, let's say, mission critical stored fuels, it all begins with sampling. Now, when it comes to fuel testing, and we're going to take a step back here and try to frame this, give some context as to why it all begins with sampling, why sampling is important. Well, if you take a step back or a step forward, depending on which way you're looking at it, and you talk about the testing aspect itself. When it comes to fuel testing in the context of trying to detect problems, people always assume, it's human nature, we assume that whatever test we selected, we selected it because we think it's going to tell us what we want to know, right? And so related to that, we assume that whatever samples we have that we're doing the test on, we assume that those samples are an accurate representation of the actual condition of our storage tank, which is the place that the samples came from. Now remember, we said very early on, where and how you sample controls what you can detect. Let's use an example. Most commonly in the retail gas station world, fuel samples are collected from dispensers. And there's reasons for this. It's fast and it's easy. Dispenser gives you a nice, good, clean fuel sample that is perfect for fuel quality testing. And fuel quality testing is stuff like measuring the cetane rating or measuring the viscosity or measuring the flash point. And all of these are important tests that have definite value to be used in things like verifying that the fuel's in legal specification. However, they're not so good for microbiological purposes. And it's very possible that if you're using a dispenser sample to try to test for the presence of microbes, then you're not actually going to have a representative sample at all. In order to detect microbes, you don't need a dispenser sample, you need a bottom sample. But even if you get that, it is still remarkably easy to get a bad bottom sample that won't give you accurate results if you're trying to detect microbes. So what are some of the hurdles here with sampling? Well, you can be hindered by the design of the tank in your sampling. What is the one thing that goes most hand in hand with microbial content in stored fuel? Well, that would be water content, of course. That means if you're doing condition monitoring and you're trying to scout out possible or detect possible microbial presence, by necessity, you are also going to be looking for the presence of either free or emulsified water content. Yet, it's not uncommon to have a storage tank that has zero detectable free water if you're measuring at the fill end. And yet if you were to go to the turbine end and do a measurement, you would find 50 gallons, 100 gallons of water sitting down there waiting to be pulled off if you actually knew it was there in order to do that. Now, reconcile this practical fact with the fact that for underground storage tanks, you have certain regulations that dictate, that mandate that the tank is supposed to be trim by the fill end, is what they say. What that means is it's supposed to be either level or it's supposed to be slightly lower. The fill end's supposed to be slightly lower because, of course, the fill end is a place that's most easiest to get water out of. So they want the water to roll down to that end. Yet, because of the weight of tanks, once they're put into the ground, they almost always settle into their backfill. And then and they settle in certain ways. Most commonly, they'll settle at the turbine end, which gives us that problem we just talked about. Tanks do not settle evenly. They settle unevenly, and how they settle affects where the water accumulates in the tank. Now, they can be trimmed by the fill end, like we were just talking about, which creates a situation I would say an ideal situation, where the water is easiest to remove there because the fill end is easiest to get at. But you could have a tank that's trimmed by the turbine end. This makes water removal a lot more difficult. You can have a tank that sags where the center of the tank is actually lower than both of the ends, which makes water pool at the ends of the tank. You can have a hogging situation where the ends are actually lower than the center line. That makes water actually pool at the intersection of the longitudinal and what they call the transverse latitudinal center lines. And it's also not uncommon at all. It's very common for over time the hydrostatic pressure, the weight of the fuel, the thousands of gallons of fuel in that tank, will actually cause the bottom plates of the tank to deform and change shape. And so if they change shape relative to the shape of the tank bottom itself, that creates spaces for the water to pool and collect over time. And the problem there is that you don't know if that's happened. There's no way to know. So how would you know where this water was and how to get to it? I mean, all of this speaks to the truth of just how much variance there can be between what's appearing in our sample and what's actually going on in the storage tank. And if it's true for something as simple as water in the ways we were just talking about, it is just as easily true for microbes themselves. So without a good sample, it is impossible to know if your test results actually do reflect the reality of the situation. So how do we get a good sample? Who defines or tells us how to get a good sample? Well, the gold standard for sampling practices are the ASTM standards. And there are two standard guides that speak directly to sampling and handling issues. D4057, the standard practice for manual sampling of petroleum and petroleum products. This is about 48 pages long, and it covers how to best collect fuel samples if you want to do specification testing like fuel quality characteristics, like the cetane and the viscosity we talked about. 4057 discusses types of sampling apparatus and types of instruments that can be used to pull fuel samples. It tells you the types of samples based on the location within the tank, like a bottom sample. What's the difference between a bottom sample and a middle sample, or an all-level sample, or spot sampling? It talks about all of those. It details sampling methods and the procedures on how best to do all those different kinds of samples. And that is especially important when it comes to the spot sampling techniques, which is really the most common one that's done for the kind of fuel sampling that we're going to be talking about. And 4057 also covers special instructions like minimizing the number of transfers between any of your primary fuel containers and any intermediate ones, because that can affect fuel specification testing if you're trying to do flash point or water and sediment. And also recommendations on avoiding undue exposure of your sample to air, which matters if you're conducting stability testing. So 4057, 48, 49 pages long. Problem is that it does not cover special issues that have to be taken into consideration if you're going to test for microbes. So that is why 7464 was created, the standard test method for manual sampling of liquid fuels for microbiological testing. That's the gold standard used for sampling that's intended to be used to do microbiological testing. And it starts out by talking about how samples for microbial testing, how they need to be prepared and handled properly to prevent both outside contamination in the sample, you don't want that, but also to prevent or minimize degradation of the sample. So the first thing we need to acknowledge with 7464 is that there is a lot of overlap between it and 4057. In fact, it references 4057 in a lot of places, especially in the guidelines for sample pulling and handling. It'll say The recommendations on how to do this were covered in 4057, so refer to that. But that being said, it does cover some additional aspects that 4057 does not, like for whatever they have deemed is necessary to know in order for you to have the best success at pulling samples to be used for microbial testing. Now, the biggest areas of emphasis that 7464 points out is, I would say, number one, the importance of the sterility in your equipment and your sample handling materials. Number two, I would say the guidelines for cleaning sampling devices in between pulling samples. And then number three, probably how to pull and handle the major kinds of samples needed for microbial testing. See, 4057, when it talks about kinds of samples, it really talks about them more in the context of areas of the tank to do sampling in, like the bottom or the middle, But 7464 approaches a little bit differently. They cover samples. I don't want to say how to say this. They don't really cover bottom or middle or top middle. They cover tank samples and tap samples. How to get a sample out of a tap from a tank. Surface samples, samples of filter media, and samples involving solid components. So a little bit different there. So between these two guides, we really have some excellent guidance on how to do this important job properly. Now, where you pull the samples from is a key towards their viability. If you pull a sample from an area of the tank that doesn't have any microbial presence, well, then your sample is going to tell you you don't have microbes. It would be a false negative, essentially. So we're trying to sample from the places in the tank where we think the actual microbial presence is most likely to be, right? Now, we've already said that microbes most like to live on solid surfaces within some kind of biofilm. So it stands to reason that if you wanted a sample that has the most chance of showing you accurately your microbial presence, you would want to do surface sampling. Unfortunately, we have issues of practicality here. It's rarely practical to get a good surface sample from a tank or from the inside of a tank, which means the next best alternative is to get a bottom sample, or what they call a three-phase bottom sample. And a three-phase sample means it's going to contain bottom water, it's going to contain some rag layer, which is that microbial biomass stuff that tends to form at the interface. And then it's also going to have some what they call near bottom fuel, which is fuel that's between about 10 and 18 inches above the water phase in that area. So in order to get a sample like this, you got to know where the water phase is. So that means you have to check for water beforehand. Typically, many of you probably know how to do this. Typically, checking for water, of course, involves water paste and a tank stick or something like what they call a sounding tape. Now, so you want a three-phase bottom sample. You also want to make sure that you sterilize your sampling tools, because if you don't, it's easy to cross-contaminate your samples. Now, the old school method for sterilizing sampling tools would have been to dip the tools in alcohol and then flame them to sterilize them. But yeah, some of you are like, I don't know about that. Yeah, the guidelines point this out. It's not really an option to flame them around fuels. So the best practice for sterilization when you're sampling around fuels is you put the tools, you dip them in alcohol, or you rinse them with alcohol solution that's at least 70%, and then you let them dry. You also want to make sure that you put your samples in unused bottles. You don't reuse sample containers. And, of course, if you use, we said sterilizing your equipment, your tools and equipment. Well, equipment also means things like funnels as well. You want to make sure that those are sterilized if you're going to use a funnel to transfer your samples. So good sampling is absolutely essential to getting as accurate a picture as possible of the realities that exist in your storage tank. We'll bring this point up again. We have a tendency, this is a psychological tendency, to believe that what we see is reality. What we see is all there is. So it is important to have good testing methods and to understand what those testing methods may be telling us, as well as what they're not telling us, if we are to have an accurate picture of what's actually going on. So once you have samples, you're going to test them in order to tell you something meaningful about them, right? Test data from samples doesn't mean anything if you don't have context, if you don't have the proper context. And context involves having standards to compare those results and so that you have a good interpretation. Typically, when we're doing something like, let's say, microbial testing, we will use benchmarks. Like we will say, if you have like 10,000 microbial units, if you're above that, typically that is an indication that there's a problem. Now, the key word there, however, is typically. 10,000 microbial units per milliliter might be a problem for many tanks, which is why they're treated as a general guideline. But that doesn't mean that's absolutely true for every single tank. Not to mention, of course, another issue, which is that's an aggregate figure, 10,000 microbes. That's total microbes. We don't actually know what kinds of microbes are making up that 10,000 figure. When you get down to it, this is important to understand. When you get down to it, every tank environment is different. Every tank in every place has a fingerprint. We have some people in our audience that are from Florida, right? Maybe from Orlando or Fort Lauderdale, whatever. Other people might be in Texas. Other people might be in Michigan. Every tank environment is different, and every tank in every place has a fingerprint. Luckily, we now have the ability to know what the fingerprints for our own tanks look like, instead of having to base our decisions on what everyone else's tanks. In other words, we have the ability to know what is or is not a problem in our own tanks, and that's really what's most important. Now, the only way to get the right fingerprint for your specific tank, now we're transitioning into genuine condition monitoring stuff here. The only way to get the fingerprint for your tank is to do trending, okay? Trending, very important. Trending requires taking multiple fuel samples over a period of time and looking at the results for those. Now, in order to do trending, you start by getting a baseline. The baseline is your benchmark, your starting point. Ideally, your benchmark or your baseline is collected just after the system's cleaned. Some people say after it's been newly constructed and goes into commission, but we know we only get one shot at that, and most people aren't going to be able to utilize that. So, baseline, collect and analyze sample collected just after the system is cleaned. You have a starting point now. You've established your baseline. Then, best practice now is to sample 3 times during the control interval for your tank. Okay. What's a control interval? What are we talking about? Well, as you get more data, right, as you get more data points over time, what you start to see trends developing of the points in time where the microbial levels in that tank, they rise. They may fall because it's not linear. They'll go up and down, but generally speaking, over time, the trend will be that they will rise over time. Now, at some point, they will exceed or rise above whatever threshold you've established or you've selected that says, okay, now we have too many microbes in there, and it's your cutoff point to take action. The amount of time it takes to go from start to problem is your control interval. Generally speaking, a common control interval for bulk storage tanks is between 6 and 12 months. But like we just said, every tank is different. It doesn't necessarily mean that yours is going to be that way. So the takeaway here is that you need to get enough data. You need to have enough data sample points often enough to figure out what your true control interval should be. Now, quick note here on chain of custody forms. Okay, chain of custody forms come into play when you're taking samples, and we wanted to mention them because they are actually important. It is always best practice whenever you're doing fuel sampling and then you're going to be testing or analyzing those samples. It is always best practice to have chain of custody documentation. That's for whenever you have a situation where you're going to collect samples, but you're going to test them at a later time and place. Now, typically chain of custody is a form, a COT form, and it gives enough information on it, has enough information to document who had the sample when, what's going to be done with the sample, and who's going to do the work. Now, acknowledging the importance of chain of custody form appropriately leads us into considering the other important aspect of condition monitoring, that is how to handle the sample properly. And along the lines here, we have to say a few things about time sensitivity when it comes to sample handling and microbial testing. How quickly you need to test or analyze whatever samples you pull depends on what you're going to do with them. Now, if you're just pulling samples to do chemical property tests, if you're just going to have those kind of property tests tested, you have more time to take action because those kinds of tests, like a stability rating or cetane value, those are not time-sensitive tests. But the opposite is true if you're pulling samples for microbial analysis. Samples for microbial analysis are absolutely time-sensitive because microbes are living organisms. And when you take a sample and you pull some of those microbes out of their normal environment, they can react adversely. And they can react and behave in ways that weaken the relationship between the test results from that sample as compared to the state of those measured parameters in the system from which you pulled the sample. Now, typically you can have three general scenarios here. Okay, so let's look at these. The first one is that you pull a sample and the microbial population in that sample doesn't really change at all. It stays stable. This is what we're really hoping for. This is the ideal one. So if the microbial population in that sample doesn't change, and this is assuming that this is a good representative sample. That's the baseline assumption here. Microbial population doesn't change. So when you get your test results, what you see is, for the most part, what is actually present in the base environment. So that's best case scenario there. But a second scenario could be that the microbes actually increase. Now, that's not ideal because what you're going to end up with is you're going to have kind of a false positive. You're going to have more microbes being detected in your sample than what was actually in your tank. That's not ideal, but the silver lining there is at least we can see qualitatively that there is microbial presence. So, okay. The third scenario is that some or all of the microbes die off. They don't like being in the sample. What this does is this leads you to a false negative test reading. You've done the test, you record no microbes, but in fact there's lots of microbes in their tank. That's the biggest problem of those three scenarios. So the longer the amount of time that passes between sample collection and testing, the weaker the relationship is going to be between what you're seeing in the test results and the actual state of the microbiome within your tank and your fuel system. So, with those considerations in mind, how quickly do you have to do microbial samples? Well, the ideal situation is you test the samples within 4 hours. Okay. If you're doing ATP testing or some kind of microbial testing on site, you can do that. But in the real world, like 80% or more of samples that someone's going to get their hands on are going to be more than 24 hours old. And this is going to be especially true if you can't do the testing yourself, if you have to send the samples off to someone else to do your microbial analysis. So that is probably what most people in your position out there in the audience are going to have to end up doing. So what are the recommendations for doing this? Well, first of all, when you're pulling your samples, it is always recommended to have a cooler with ice so that you can put your fuel samples in there after you pull them and you put them in the containers. You put the samples in clean, unused sample containers that are either glass or clear plastic. Then you seal them up, you put them in the cooler, and you transport them wherever you need to go. Now, again, if you're going to do microbe testing yourself, then you can test them within the 4-hour window, and that's great. But most commonly, you're going to send them off to a third party for microbial testing. If this is what you're going to do, then you'll want to put the samples in the refrigerator until you're ready to package them up, preferably the same day. Again, time is of the essence here. It is very important to slow any additional microbial growth that's growing on, and the best way to do that is to keep them cold. But the one thing you do not want to do here, you see it on your slide, is you don't want to freeze them. You do not want to put the samples in the freezer because the process of freezing and thawing will almost always kill off at least part of your microbial population. You don't want that. Now, packaging samples for lab shipment. There are specific guidelines on how to best ship fuel samples. Typically, these guidelines and requirements require you to use things like absorbent materials and sealable transport bags so that if your sample happens to leak in storage, it's not going to contaminate everything. Now, we here at Bell Performance, we do this kind of testing all the time through the Bell Fuel and Tank Services program. And we actually have prepaid sample transport kits. Typically, those are insulated boxes, and they contain everything you need to properly package and ship your samples. So you've got prepaid shipping box that's insulated. It's got absorbent material and bags. It's even got cold packs that you put in the freezers and then put them in the box in order to help keep them cold. A lot of people just find it easier to buy these from us and then ship them back to us for us to do the testing because the cost for these also includes the cost for doing the test and reporting the results back to them. And then, of course, what we generally tend to do is we also can assist with the data record keeping and the trending of the information, should that be something that you deem is necessary for you. So, all of these things that we've been talking about in the last hour, those are the essential considerations that all stored fuel users need to know about condition monitoring of their stored fuel and fuel systems. These are especially important to keep in mind for those of us out there that are involved with mission-critical stored fuels. So just to review quickly, what did we cover in this webinar? Well, after we went through and talked about the basics of fuel microbiology, we dug into condition monitoring. That means proper sampling guidelines, proper handling procedures, because, remember, sampling controls what you see, so it is imperative that your samples are obtained using best practices. Then for microbial testing, if you're pulling samples in advance of microbial testing, you want to pull 3-phase bottom samples that contain water and biofilm and some of that near bottom fuel that's 10 to 18 inches above the water layer. We talked about how important it is to take samples over a period of time because that allows you to see the trends that go on in your specific tank. That helps you to determine your specific control intervals that represent the fingerprint that's unique to your tank and your fuel system. And, of course, proper sample handling, including keeping samples cold and getting them tested as quickly as possible. That plays a key role in making an accurate determination about the state of your fuel and, very importantly, what you need to do next because, that's the thing, right? You want to know if you have a problem, but it's also important that you don't waste time, waste time chasing your tail if you don't actually have a problem. And doing things like this, doing like some of the things that we discussed, are the best chance to help ensure that you don't do that. And so it goes both ways there. So we've covered an awful lot over the course of this. Hopefully, beyond some useful tidbits about fuel microbiology and important aspects of condition monitoring, we also hope that you've come away with a better sense that the whole issue of microbes in stored fuel is a lot more complicated than it may have first seemed. Microbial contamination monitoring and controlling that is a never-ending process. It's not something that you do once and then you're done. It requires you to pay attention both in preventing problems and then fixing problems when they're found. And we are actually going to discuss that topic in more detail in our next Bell Performance webinar, where we're going to talk about, it's kind of like the part 2 to this. We're going to talk about proper testing of those samples, how to interpret that, and then contamination control, what the best practices on what you need to do next. So, given the amount of information that we've covered, I know we're running up on probably an hour and 10 minutes here. We know that there are questions. I don't know that we're going to have enough time to take questions here at the end. So, and there's always a chance of that happening and things like this. My contact information is on the screen. My email there, ebjornstad@bellperformance.net. If you have any questions, absolutely give me an email. And what we'll do also is whatever questions we get, we will compile the answers, and we will, unless you tell us you don't want us to pass to reference your question, we will kind of put together the questions and answers and send them out to everybody so that everybody sees what the answers are and maximizes the value that you get out of it. So my contact information is on the screen. Please touch base with me with your whatever question you have. Many of the action steps that we've covered in this webinar are things that we do in normal practice with Bell Fuel and Tank Services, especially all the microbial sampling and testing services that we talked about. The goal with the Bell FTS program, the goal is really to make this whole process as easy and also cost-effective. Cost is always a consideration. So easy and cost-effective as possible for our customers, because we understand that there is a lot more to think about in taking care of mission-critical stored fuel and storage tanks. There's a lot more to think about than there used to be. Many times we know it's helpful to have a partner that can come alongside you and help guide you through the process in whatever capacity you need them to. So if you're listening to that and that sounds like, hey, that's kind of like the situation that we're in, then I would encourage you, absolutely, touch base with me and we'll get a dialogue going. We'll get a discussion going on what you need and how best to get you what you need versus what you don't. So thank you. Thanks, everyone, for joining me. Keep an eye out for our next webinar. That will be probably in September, where we're going to go into more details about condition testing and contamination control issues. So once again, I am Eric Bjornstad with Bell Performance. This has been our webinar on condition monitoring for stored fuel. Have a great day, everybody.